Okay, I know you guys are pretty keen to get a little bit of a video happening with Eulers, or as most people seem to call it, Eulers. It is actually Euler's method. Basically, the reason we use Euler's method in this case is if we have a function that we can't integrate, this is a method that allows us to sort of trace back from an initial point that we know. So if we've got an initial condition, we can't integrate the function, we can still get an approximate answer for a value of the original function without actually knowing what the integral is. So what I mean by that, if we have a gradient, like if we're given a gradient function dy dx, and we know when x equals 0, y equals 3. And we're like, so we know what our gradient is, and we know when x equals 0, y equals 3, we would have a point here which is 0, 3. Now what we do is if we know what the gradient is at the point 0, like we can sub it in, if we create a line, or like I guess it's a tangent, yeah, it is a tangent to the original function, because it's the gradient of the original function, so the original function might look something like this. That line is a tangent at the point 0. What we do is we use that line, we go from the point 0 to some other point just to the right of it, or it could be a big distance. The shorter the distance, the more accurate it is. So if I move h to the right, and then I find out what this point here is. So just say this is our original equation. Like we don't know what it is, but that is our original equation. We've got the gradient for that equation. We use the point that we know, the initial condition, which in this case was 0, 3. We find the equation of that tangent. We then use a point, like we use a value of h to the right, and we then find this new value. So we'll call this point here x0, y0. Why am I doing it so far out? Oops. So that's x0, y0. And then we've got another point here, which we call x1, y1. That's our new value. And then we use this value and the fact that we know what the gradient is to then create the gradient of this thing here, of the original equation, would be like that. So that's a tangent. But if I use the tangent here and create a line, and then I go to another point, which is a further h to the right, so I go h further to the right, we then get another value. And that's based on, so we start using this condition, which allows us to find out this value. Then we use this value, which allows us to find out this value. And then again, we use the gradient, because we've got the gradient function, and we create a tangent again. So that would be the same as the tangent here. So those two tangents would be the same. And then we move h to the right again, and then that will give us another approximation. So this is what the actual value would be if we knew what that function was. And this is what we get using tangents and values of h that trace back on the curve. So they're basically tracing the curve backwards using a numerical method, so a repetitive method, to get an approximation of what the function would be. And eventually, like if I said to you x0, y0, and if I said to you when x equals 1, what does y equal? Well, if we used h values of 0.2, we would first we'd go from x0, x equals 0, x0, which is x equals 0, and y equals 3. We would then get x1, which is 0.2, because my h value, my difference is 0.2. x2 would equal 0.4, x3 would equal 0.6, x4 would equal 0.8, and x5 would equal 1. Whatever our y value is in this case is our approximate value of what y stupid pens run out. That would be what y of 1 is equal to. So y of 1, when I put 1 into the original equation, what I would get. So let's have a look at this. I can't rub out with my finger. Why won't I rub out? No. Okay. I've got some charge back in the pen. I didn't realise it was that flat. Okay, so here, if we have a look, Euler's method, y dash is our function. We call that our function. We're given an initial condition. We use this to work out our, sorry, we don't use that. We use this function here. So y1 is based on my previous value plus h times my derivative at the point x0, y0. Now, if it was just a function of x, it would just be f of x0 or f of x. Generally what we want to say, so if we had to say it, if it was a function, if dy dx is a function of x, then we would say y n plus 1, my next y value is my previous y value plus h times f of x n. So substituting xn into that function, multiplying it by h, and then to get our next x, for our yn plus 1 is given by that there, so using that equation, and our xn plus 1 is just my xn, my previous x value, plus h, so the difference between each time we evaluate x. So that's if it was a function of x. If dy dx was a function of y, then our equation would be yn plus 1 is equal to yn plus h f of yn, so we substitute our y value in. Then yn plus 1 would be given by this equation, and xn plus 1 would be given by xn plus h. So this would give you my next y value and my next x value. And if I had a function of both, dy dx was a function of x and y, then our next y value is given by my previous y value, so yn, plus h times f of xn, yn. So yn plus 1 is given by this equation. Xn plus 1 is always xn plus h. So that's what this here is. It's basically the formula to find your next set of values. So it's called an iterative method. And an iterative method means that you're using repetitive steps, iterations, to find out an initial value. So it's not exact. It is an approximation. However, it does give you a reasonable idea, but it won't give you an exact answer. Now, it may seem stupid, but with this question, the reason you use these numerical methods is because you can't integrate a function. But then in my example, I've used a function which we know how to integrate. The reason I'm doing that is to show you why the method works. Okay, so first thing here, solve the differential equation y dash is equal to 3x squared, y1 is equal to 1, and evaluate y of 2. So what we're saying is we know what the derivative is. We know that y dash dy dx is equal to 3x squared. We know in the original function y, when x equals 1, y equals 1, and I want to find y of 2. So if I couldn't integrate it, I could use this iterative method, Euler's method. So what I'm going to say, we're going to do the exact first. So I want to find the exact answer. So here's A. we've got the integral of 3x squared dx. So we know that that's equal to y. So we can say y equals x cubed plus c, because we integrate this and we get a constant. And we know y of 1 equals 1, so we get 1 equals 1 cubed plus c. So c is equal to 0. So our original function is y equals x cubed, and we want to evaluate y of 2. So y of 2 is 2 cubed, which is 8. So because we could integrate the function, we could actually find what the exact value y of 2 is. Now if we use Euler's method to approximate with y of 2, so we want to find y of 2 with steps of 0.5 and then steps of 0.2. Now 0.5 isn't going to be as accurate as 0.2 because we're using bigger values of h, so it doesn't trace back as well. But let's have a look. I'm going to move this, like our solution, over to here. So we know for a, y of 2 is equal to 8. So that was our exact value. Now if I use h values of a half, so let's say b. Now we know our initial condition, x naught is equal to 1. That comes from here. Y naught, our initial y value, is equal to 1, and that comes from here. We want to find y of 2. We know that our h value is 0.5, so h equals 0.5. Now Euler's formula is yn is equal to, yn plus 1 is equal to yn plus h times f of xn, yn. Because this is only a function of x, we can just make it f of xn. Okay, so we know I want to find y2, my second y value. So I want to find y1 because I've got y0, I need to find the next one. So y1 is equal to y0, my previous value, which is 1, plus h, which is 0.5, times f of xn, which in this case xn is 1. So I want to find 3x squared. But in this case, we know that x is 1 because it's x0 squared. Okay, so we've got 1 plus 1/2 times 3, which is 1 plus 1/2 times 1/2 of 3 on 2. 1/2 of 3 is 3 on 2. If I add them together, I get 5 on 2. So we can say y1 is equal to 5 on 2. And we can say x1 is equal to, x1 is x0 plus h. We know that x0 is 1, and we know that h is 1/2. So 1 plus 1/2, so x1 is 3 on 2. Okay, but we want to evaluate y of 2. That's not 2, that's only 1.5. So then to get our next value, we get y2 is equal to y1, which is 5 on 2, plus h, which is 1/2, times f of x0, x1, because this is y2, we use x1, so 3 times 3 on 2 squared, which is 5 on 2 plus 1/2. 3 times 3 on 2 squared. 3 squared is 9, on 2 squared is 4. We've got to times it by 3. I get 27 on 4. So here we end up with 5 on 2 plus 1/2 of 27 on 4, which is 27 on 8. If I want to add them together, I have to make that on 8 as well. So I'm going to say plus. I'm going to put 8 on the bottom and 20 on the top. So I end up with 47 on 8, or how many 8s go into 47? 6 8s are 48. So this is going to be 5 and 7/8. So that's our approximate. Now we know that we know that y2 is equal to 5 and 7/8, and we know that x2 is equal to x1, which is 3 on 2, plus our h value, which is a half, so that's 2. So when x equals 2, y equals 5 and 7/8. Now our real value is 8, so it's not very accurate. Okay, so that's not that close to that really. Now the next step, so that's I. If I do II, Captain, did you get it? Now we do it with a h value of 0.2. Now it's going to take longer because if I go from 1 to 2 and I have h values of a half, it's going to take 2 steps. But if I go from 1 to 2 and I use a h value of 0.2, I'm going to go 1, 1.2, 1.4, 1.6, 1.8, 2. So I'm going to do 5 steps. So this method's going to take longer, but it'll give you a more accurate solution, or we can test it. So x0 is 1, y0 is 1, y1 is equal to y0 plus a h. Now h in this case is 1/5, not a half. F of x0, so it's going to be 3 times 1 squared. So I get 1 plus 3 on 5, because that's just going to be 3. So 8 on 5. So we can say y1 is equal to 8/5. X1 is equal to x0 plus h. We know that h is 1/5, so 1 plus 1/5, which is 6/5. Okay, then we want y2, which is y1, 8 on 5, plus h, 1/5, times f of x1. So that's going to be 3 times 6 on 5 squared, 8/5, plus 6 on 5 squared, 6 squared is 36, times 3 is 108 on 5 squared. So that's 108 on 25, but then when I times it by a fifth, I'm going to get 108 on 125. So I need to times this by 25 to get the same thing. So I'm going to get 200 and on 25 plus 108 on 25, which equals 308 on 25. So that's y2. That's 308 on 25. And then x2 is going to equal 6/5 plus another fifth, which is 7/5. Now, so I don't have to keep doing the mathematics behind it, I'll show you how you do it on a CAS. So, first thing we want to do is we want to define f of x to equal 3x squared, which is our original function. We know that our next value, so our next f value is 1 plus 1 on 5 times f of 1, because we know y0 is 1 and x0 is 1. So we get 1.6. I'm going to change it so that it's exact. So I get 8 on 5. Okay, so when we want to evaluate the next one, that will be our previous y value, which is this one, 8 on 5, plus a fifth times our new x value, and our new x value is 1 plus a fifth, which is 6/5. So that gives us 308 on 125, which is what we got here. Well, that's supposed to be a 1. So now I know y2 is 308 on 125, and x2 is 7 on 5. Now I want to work out y3. So y3 is going to be my last y value plus 1 over 5 times f of 7 on 5, my next x value. So here I did 6 on 5, now I do 7 on 5. I get 91 on 25. So y3 is 91 on 25. And is that right? 1/5 f of 7 on 91 on 25. Yep, looks like it's right. Okay, my next x value, I've got to add a fifth to that, so I get x3 is 8/5. So then I use that in the next part of the question, 91 on 25 plus h, 1/5, times f of my new value, which is 8 on 5. That's my next x value. 647 on 125. So I get y4 is 647 on 125. My x4 is going to equal one more than that, so 9/5. Okay, so then we go one more. So 647 on 125 plus 1/5 times f of 9/5. So each value is always worked out of, each new value is worked off the previous value. So I get 178 on 25. So y5 is 178 on 25. And then x5 is equal to 2. We want to find y of 2. And we know that x, in this case now, is equal to 2. So y of 2 is equal to 178 on 25. So here I had 5 and 7/8. That was my first value. So 47 on 8. So that was using 2 steps. We get 5.875. But then I get 178 on 25, which is using 5 steps. And you can see we get 7.12. So y5 is equal to 178 on 25, which is 7.2. Now, if I said to you which one's more accurate, well, we approximated 5 and 7/8. With 5 steps, we ended up with 7.2, and our original is 8, like that's the real value. So you can see when you use more steps and more h values, you end up with a closer approximation to what the actual value is. Okay, so the more steps you use with Eulers. So really, what the calculator does is when it integrates hard functions, like if it doesn't know how to integrate them, but it can show you what the graph is, what it does is it's using really small values of h, and then it just plots them as dots, and it pretty much just traces back and creates the function using an iterative method or a numerical method. So someone said to me the other day, oh, what's numerical solve versus just real solving? Well, numerical solving is when it's using an iterative method and it's using approximates to try and get what the actual solution is. Okay, so now we've got a function, which in this case is in terms of x and y. So we do exactly the same thing we did before. It says to use steps of 0.5, and I want to find f of 3, and I know when x equals 1, y equals 0, so that's our initial condition. So we'll start off by saying x0 is 1 from here. y0, that's not a y. y0 is 0. We know that h is a half, and we want to find f of 3. So we want to know when xn equals 3, what does yn equal? Now we know because we're going from 1 to 3 and we're going with a step value of h, we should know that we're going to have 4 steps. Because from 1 to 3, there's a difference of 2, and if we divide it by 0.5, we get 4, which is 4 steps. Okay, so remember yn plus 1 is equal to yn plus a h times f of xn yn. So this time we need to use both our x and y values to find our next value. So we say y1 is yn, which is y0, which is 0, plus a h, which is a half, times f of xn yn, and in this case it's x plus y. So I say x, which is 1, plus y, which is 0, and that gives me y1, that's 0, that's 1, so it's going to give me a half. So y1 is equal to a half. x1 is my previous x value, which is 1, and then plus a half, which is 3 on 2. Okay, so if I want to find y2, that's y1, which is a half, plus h, which is a half, and then f of x plus y. Because in this case, f of xn, yn, is equal to x plus y. So if I put x in from my previous question, I get 3 on 2 plus y, which is 1 on 2. So we end up with a half plus 3 on 2 plus 1 on 2 is 2. A half of 2 is 1. So I get y2 is equal to 3 on 2. x2 is equal to my previous x value, which is 3 on 2, plus 1 half, which is 2. So bring that up. y2 is 3 on 2, x2 is 2, y3 is y2, 3 on 2, plus a half times f of x plus y. So add these two things together. 2 plus 3 on 2. So I get 3 on 2 plus a half of 2 plus 3 on 2 is 7 on 2. So I get 3 on 2 plus a half of 7 on 2, which is 7 on 4. If I put that on 4, the top becomes a 6. So I end up with 13 on 4. So we end up with y3 is equal to 13 on 4, and x3 is equal to x2, which is 2, plus h, so 2.5, that's 5 on 2. Now our next value is going to be our answer, because we've done 1 step, 2 steps, 3 steps. We know y4 is our answer. y4 is equal to y3 plus a half times these two things multiplied together. So 13 on 4 plus, I'm going to put that on 4, so 10 on 4. So I get 13 on 4 plus, I'm going to get 23 on 4 times a half, which is 23 on 8. If I add them together, I'm going to have to make that an 8, which means the top becomes 26. So I get 49 on 8. So therefore y4 is 49 on 8. x4 is equal to my previous x value, which is 3 on 2, plus a half, which in this case is 2. So when x equals 2, y equals 49 on 8. So that's our approximate value for y. Sorry, that's 3. What a stuff up. How did I do that? Oh, my last x value is 5 on 2. So this value here is 5 on 2 plus a half, which is 3. So when x equals 3, y equals 49 on 2. So y of 3, 49 on 8, is equal to 49 on 8. So that's our solution. Okay, so let's do it using the last method on the calc. Okay, so I'm going to define, we can't define f of x plus y because it's not a function. Okay, so we can say our original y value is 0 plus our step value, which is a half, and then x plus y, 0 plus 1. So we get a half. So our next value is a half plus a half times my last y value, which was a half, plus my x value, my original x value, which was 1. Oh, that would now be 1.5 because I've added a half to it. So I get 3 on 2. My next value is plus 1/2, and then times 3 on 2, my last y value. My new x value is going to be 2, because 1.5 plus 1/2, which is, oops, plus 2. So that gives me 13 on 4. My next value is 13 on 4 plus a half, my h value. My y value plus 2 plus a half, which is 5 on 2. So that gives us 49 on 8. So I've got 5 on 2 plus a half, my h value, my last y value, plus 5 on 2 plus... Was our answer 49 on 8? Our answer was 49 on 8, so we've already got to the answer. Because when we got to here, if I get 49 on 8, if I want to get my next x value, that's 5 on 2 plus a half, which is 3, so my solution is 49 on 8. So we've done, that's 1 step, 2 steps, 3 steps, 4 steps, which brings us to x equals 3. So that's our solution. I do have another... We have an e-activity called Eulers, but I can't put it on the CAS on here. Okay, so basically, all you need to use Euler's method, which is in your notes, you need your initial x, you need your initial y, and you need dy dx, which is your function. And then you can plug that into Euler's method. And if you wanted to, you could use your differing values of h. The smaller the h, the more accurate the answer. And that's because when we create these tangents, if I created a tangent that went all the way to here, and then I did it again, and then I did it again, if I instead created a tangent, let's make it pink. So if I created a tangent, where'd it go? Where'd it go? Okay, so if I created this tangent, there's my tangent. Instead of going all the way across to h, if I just went to here, like a smaller h value, if I made my h really small, and then I created another tangent, and then I did the same thing, created another one, you can see that as I create tangents, it's going to stick closer to this line than if I have big values further away. They're going to move further away from that line. So the smaller the h value, the smaller the difference between each tangent, the quicker it's going to, it's not the quicker, but the more accurate it's going to be in actual sticking towards the real curve. And likewise, if you have a function that goes up and then curves back down, if you've got big h values, they can actually move like really far away from the curve. Whereas if you're following the curve with little h values, it'll follow it much nicer. So the more h values, the more accurate it is. Generally, in a calc-free SAC or in an exam, they would get you to do something like this question here, which is 2 steps to find out what you want to find out what the value of a function is using 2 steps of Euler's method. Okay, so 2 steps of Euler's method is usually all you need to do by hand. You can do it on the CAS otherwise. I've also got that function that I'll put on your CAS, so if you've got a CAS, it'll just spit out the answer for you, and I'll show you how to use that if you need some help with it. Okay, have a good weekend. I shall see you Monday.